Let's start with a recap. Okay, so we are continuing our discussion on relations, and yesterday we started our discussion about different ways by which we can combine relations, and therein we discussed that all the operations, set operations, union, intersection, difference, set, symmetric difference, all operations that we perform on set can be performed on relations as well. And the reason is because relations are also sets, and it's a special kind of set which consists of ordered pairs. After that, we started a very interesting notion about closure of reflection, closure of relations, and what was the notion behind this closure. So basically, we motivated it with an example that if suppose we are given a relation and it does not satisfy some property, say reflexive property, symmetric or transitive property. Okay, so what is the minimum possible addition of ordered pairs that you can do so that you can make the smallest possible reflexive, symmetric or transitive relation? That was called the closure of that relation. Specifically, if I talk about a reflexive closure of a relation, it included all such kinds of diagonal elements a comma a which we are not currently in R. So any diagonal or identical element a comma a which is missing in R, if you add them, all such pairs, then you make the relation as a reflexive closure. Similarly, for the symmetric closure of any relation R, what you need to do for any ordered pair a comma b, if its inverse b comma a is missing, you add that for all such elements, and once you add all those inverses, then the resulting relation is known as symmetric closure. So basically, whatever is missing out of the symmetric pairs, if you add them, the resulting relation is a symmetric closure relation. Similarly, the last closure that we discussed was a transitive closure, which basically consists of all the transitive pairs, the minimum possible transitive pairs. And we saw that the general formula to compute that is you take the union of R, and where till what should I take the union of R? In general, it's infinity, but if I have a finite element set, okay, suppose with n elements, then what should ideally you should take the power, very good, till n. That is, if I'll take R union R square till Rn, whatever is the size of that set. Okay, so suppose the size of the set I want to define relation on is just 2, right? So I'll take R union R square. If it was suppose 3, then I'll take R union R square union R cube, right? And how do we get these powers of relation? How can we find the powers of a relation? Yes, this is something also we discussed yesterday. We generally find the powers of relation using Cartesian product. Do we find it using Cartesian product? Yes, class? No, we find it using, very good, composition of relations, right? The power of sets is found using Cartesian product. The power of relations are found using composition. That means if I want to find a relation R square, I can find it R composition R. Similarly, if I want to find R cube, I will find R square composition R. Okay, and in general, Rn can be found Rn minus 1 composition R. Right, so the power of relations can be found using composition of relations. Right, and the last thing we discussed yesterday was an equivalence relation. Okay, so what is an equivalence relation? When do we say a relation is an equivalence relation? Yes, so it needs to satisfy 3 properties. Right, so it needs to be reflexive. Yes, class, what are the other properties? Because we are going to see some similar kinds of relations today, so it should be clear. Equivalence is reflexive, symmetric, and transitive. If all 3 of them are there, then you say that it's an equivalence relation, right? So that's where we ended. We also discussed equivalence classes, but that's where I'll start today. So let us now in today's lecture discuss more about something called equivalence classes, which are going to be some sort of division of a set if it follows the equivalence relation. And then we'll see some special kinds of relations, okay, which will be satisfying combination of these, and we'll see why they are important. Okay, so let us start with equivalence class first. Okay, so as I had given you the motivation yesterday, what is an equivalence class? So what you have is you have a set, okay, which consists of some elements, and on this set you define some relation, okay, and if this relation is an equivalence relation, okay, which means it is reflexive, symmetric, and transitive, then what you can do, you can define equivalence class of this set. Okay, so what are you given? You are given a set, okay, on which you are defined a relation, which is an equivalence relation. So these are the requirements. And once you have this relation defined on the set, then you can define equivalence class of this set. Okay, and how can you define that? What you do is you pick one of the elements from this set, okay, you denote them by square brackets, and then all the elements which are related to this element in the equivalence relation, you mention them. Okay, that set is known as an equivalence class of this set. Okay, so since equivalence relation is reflexive, is symmetric, and is transitive, so all these elements which are related to this X via these relations, you have to add them in this set. Okay, and that kind of set is known as your equivalence class. Like I gave you the example yesterday. Suppose set A is your entire batch, okay, and I define a relation R that two people X and Y have graduated from same high school, right? So since it's just a binary relation, so even if there are 10 students from same school, but I'll have it in pairs, like X is graduated from school Y, X is graduated from school Z, which also means Y is graduated from school Z, right? And I'll simply list all these ordered pairs, right? Now, what is an equivalent class? Now, if I pick one of the elements, suppose X, and I say, what are the students who have graduated from the same high school? So, what are the elements here? Yes, what are the elements? You have Y, you have Z, because they are related to X via this relation. Okay, so that set of or subset of A, which represents those elements which are related to this element X via relation R, that forms its equivalence class. Okay, so since the relation is reflexive, so what are we guaranteed? One of the members which is guaranteed to be always present in the equivalence class of X. Can anyone tell me? What is one element which is, if I make equivalence class of say some element X, even if you don't know the entire relation, but there is one element which you know for sure will be there in this set. Excellent, Usad. X. Why? Because since equivalence relation classes are defined on equivalence relation, and we know equivalence relation is reflexive, so we know for sure X comma X is always in R. So we know for sure one of the elements in the equivalence class of X is the X itself. Right? Is this clear? Right? Does this make sense? Right? Because of the reflexive property. Right? Now let us see more formal definition of it. So given a R to be equivalence relation, okay, as I said, this is important, only then you can define equivalence classes. On set A, the set of all elements which are related to element A of A is known as the equivalence class of A. Okay, and in general, you represent the equivalence class by square brackets, and inside square brackets you write the element for which you are going to compute the equivalence class. Okay, and sometimes you write subscript R if there are more than one relation. If you have just one relation, then you can skip this R. Okay, so if I define formally what is A is subset of all the elements S such that A comma S are in your relation R. Okay, and where R is always an equivalence relation. Okay, so what is equivalence class with respect to element A? The equivalence class with respect to element A is set of all the elements A comma S such that there is a pair or they are related via the relation R. Okay, so this is some set, right? So just to give you an example, suppose the set was A comma B comma C. Okay, then if you pick any element from this set, that element is known as representative of this equivalence class. Okay, so I can say A is the representative of equivalence class A. Similarly, I can say B is the representative of equivalence class A. Similarly, I can say C is the representative of equivalence class A. Okay, so what does representative mean? Representative of any class is the member of that class. Okay, and there any member can be the representative. Okay, it need not be the same. Okay, so let us see some examples to get a hold on it. So suppose I give you the following relation R on the set S. Always remember, first thing you need to do is ensure that R is equivalence relation. Okay, if it is not equivalence relation, then the question is not valid. Okay, then you cannot answer this question. Okay, so is this relation an equivalence relation? Yes, class, is this relation an equivalence relation? Excellent, it is, right? Because why is it reflexive? You have 1 comma 1 there, 2 comma 2, 3 comma 3, so it is clearly reflexive. And for all the ordered pairs of form A comma B, B comma A is there, so it's symmetric. And it's transitive also because 1, 2, 2, 1, 1, 1 is here. So all possible transitive pairs are also covered. Okay, so fine. It is an equivalence relation. So that means now we can proceed to this question. Okay, so always check the relation is equivalence or not. Now, second is, what are the equivalence classes of 1? Okay, so what are the equivalence classes of 1? Remember equivalence class? Equivalence class of element A is set of all those elements S such that A comma S is in R. Right? So what are the elements which are related to this? Excellent. 1 and 2. What about 2? 2 is also same, right? 1 and 2. Right? That's it. And what about 3? Excellent. Okay, so let me take some little more complex relation. Okay, now if I just add these two pairs here, so what all should be modified? Will this be modified 1? Will the equivalence class of 1 be modified? I have added two more pairs, 2, 3 and 3, 2. Will equivalence class of 1 be modified? No. Why? Because 1 is related only to 1 and 2. There is no relation of 1 and 3. Oh, it's not equivalent. So I have 2, 3, 3, 2. So what is the missing pair? I see. Is it fine? Abhay? Okay. Okay, so is now 1, I see. That's a good catch. Now is it fine? I think now all pairs are covered. Right? Okay, so now any modifications? That was a good catch, thank you. Any modifications here? So what are the elements associated with 1? So you have 1, comma 2, comma 3. Similarly, 2 is now also associated with 3 because you have a pair. And what about 3? Right? Very good. It is 1, comma 2, comma 3. Okay, so all the equivalence classes are same. Right? And we'll see why these properties. Okay, why they are all same, or why are they kind of different from each other? There are no common elements. Okay, we'll just shortly see why is it so. Okay, but before that, let us see some more examples. So suppose I tell you what are the equivalence classes of, we already know congruence modulo is a equivalence relation, right? We discussed that yesterday. So first check is done. Now, suppose I ask you what are the equivalence classes of 0 for congruence modulo 4, that is this relation. Okay, so what we need is 4 perfectly divides a minus b. So can you tell me on integers? Can you tell me what are the equivalence classes of 0? You have to see all possible values of a and b such that they are perfectly divided by 4. Can you tell me what are the equivalence classes of 0? Excellent. Right? So it's basically multiples of 4 on both sides of the number line. So you have minus 8, minus 4, 0, 4, 8. Okay. Okay, now what about 1? Okay, 1 means it should leave a remainder of 1. Right? When you divide it, it should leave a remainder of 1. It shouldn't be tricky, you just have to use the same set. Yes, others also, Aseed has written. Anyone else? Okay, so in general, if you write it in this notation, so we is it clear to everyone how we are getting the two equivalence classes? Okay, so what we have is 4n plus 1 and in integers, and if you look at in this manner, it's minus 7, minus 3, 0, 1, 5, and so on. So on the positive side, you have a plus 1, and here you get a minus 1, right? Yes. Okay, so okay, great. So let us see this last example, and then we can move further. Okay, is this clear? This example is clear to everyone how this is multiples of 4 and how you got this one? You have to just see all numbers which are perfectly divisible by 4, which we know will be multiples of 4. And since it's an integer, so you consider all the multiples of 4 where n is an integer. Similarly, here we want to leave back a remainder 1. So we basically want they should be divisible by 4, but leaving a remainder 1. Right? And in the number line on both sides, you will get this form. Is this clear? Both the examples are clear? Yes, no, class? They always get a reply from handful of people. Okay, great. So let us move to last relation, which is an equivalence class. So since it's already given that it's an equivalence relation, so it's fine. Equivalence class of string 0, 1, 1. So we want to find the equivalence class of this string 0, 1, 1 with respect to a equivalence relation R3 such that two strings S and T belong to R3 if S and T are either equal or S and T at least have 3 bits common. Okay, so you have the elements as strings. We say that the pair of strings ST belongs to this relation R3 if either they are equal or their first 3 bits, at least the first 3 bits are same. Okay, and we want to find with respect to 0, 1, 1, 1. Okay, so since we are focused only on first 3 bits, so what should be the relation, this set? Okay, either it is same or it is first 3 bits are same. So what would be the possible set of strings? So I've tried to use examples which are different. Okay, one was given a relation, second was using some defined property, and third is on string. So it's not numbers, now these are strings, which is more closely related to our computer science. Okay, what would be your possible string? Okay, it will be set of all those strings which are either equal to this 0, 1, 1, or they have first 3 bits same, right? So can you tell me what will be the equivalence class? Yes, class? Come on, give it a try. I mean, just understand what is the problem. It may be wrong, it's fine. Okay, let's start with the smallest one. Okay, if something has to be its equivalence class, what is the element we know for sure will be there? We discussed it in the beginning, right? If I want to create equivalence class of X, right? What is the element that is for sure going to be the part of this set? X, right? So in this case, we know for sure one of the elements is 0, 1, 1. Okay. What else? What else? We need strings which have first 3 bits same, right? So I can have 0, 1, 1, 0. Yes, it's simple. 0, 1, 1, 1. And then I can keep on growing it. 0, 1, 1, 0, 1, or 0, 1, 1, 1, 0. And I mean, I can have plethora of combinations. Okay, the main focus is it's either equal or first 3 bits are same. That's it. Right? So you can have all sorts of strings which are exactly equal to this, or first 3 bits are same. What is beyond is not of your concern. Okay, is this example clear? Is this example clear to everyone? Okay, so in general, you can see the question can be in different forms because equivalence class has a role to play in different fields. It could be directly numbers, it could be strings. I can also give you alphabet. Okay, so suppose I create an example on my own. Suppose I tell you I define a relation R, which are the words in a dictionary. Okay, and assuming it's a equivalence class. Okay, I tell you the relation is that the first letter, at least the first letter of the words are two same. Okay, at least the first 2 letters are same. Okay, now if I tell you to form the equivalence class of AN, what will be the possible thing? Relation is either they are again equal or first 2 letters are same, right? What would be the possible elements of your equivalence class? Right. So AN would be there for sure, and then anything starting with AN. Okay. Now, why AN, B, N, C won't be there? Since I said words in dictionary, so they should also have some meaning, right? So in general, it would be some meaningful words like ANI or AN, B, E, or say anonymous, whatever words. anger, whatever words start with an, but they're also part of dictionary. That is important, right? Because that's where the relation is drawn. Okay. So this was just to show you that it's not just about numbers. It's about, it can be anything which can be represented as a set, and we have a valid equivalence relation defined on it. Okay. Is this clear? Yeah, this is clear. This has this has extreme importance in programming. Okay, and I'll discuss that at the end, but this has extreme importance in programming. Just to give you an idea, like if you have ever noticed when you studied C programming, a lot of compilers, if you give remember what is an identifier? Does everyone remember what is an identifier in C programming when we discuss? Yes, it's the name we give to our objects or elements in C, right? Now, in general, a lot of machines, what they do, they take the identifier as the first 8 characters. Okay, so in such a case, this equivalence class is false. That is, if you write any identifier name beyond 8 characters, so it is, suppose I write some name which is 8 characters, and then I write another name whose first 8 characters are same, but remaining are different, right? So a lot of such compilers, they will find it invalid, because remember, one of the properties for identifier was that it should be unique in the scope of program. Okay, so that is the practical example where equivalence class is related to our programming. Okay, is that clear? We'll be discussing this more when I will come to practical applications in CS. But is this clear, the overall idea how it's relevant? Okay, excellent. So let us move further then. Okay. Now we come to another very important aspect of these equivalence classes, that is their relation between partitions. Okay, so before we see the relation between the two, let us first see what is a partition. Okay, now what is a partition? In general, we define partition of a set. Okay, so we have a set S, and what we do, we partition it, we split it up. Okay, and suppose we split it up into different components AI. Okay, where I are the indices. We split it into non-empty sets, which have actually these 3 properties. There's a typo. The properties are, first is that each of these partitions should be non-empty, okay, which is defined in the definition. Second is, each of the partitions, their intersection should be 5. Okay, if their intersection is 5, what kind of sets are these? If I have 2 sets whose intersection is 5, excellent. It is, yes, very good. Very good. These are disjoint sets. That means the partitions which we have of a set, they should always be disjoint. They should have no common element. Okay. And if you take their union, if you take union of all these partitions, it should give you the set back. Okay. So we say a partition P of S is what? It's a collection of non-empty subsets, okay, whose intersection is 5, that is they are disjoint, and their union gives the set back. Okay, so you can see best from this example, if this outer circle blue disk is our set S, you can see it has been split into 9 disjoint subsets. Okay, and you can see none of them are overlapping. Okay, each one has their own area. Okay, but if you take the union of the set, it gives you back the set. Okay, that is your partition. Okay, if you have a set S, you divide it into subsets which are disjoint, that is, they have no overlapping part. And if I take all of their union, it covers the entire set. Okay. So let me just try to see if you have understood or not. So I'll make some diagrams. So suppose this is my one diagram. Okay. So is figure 1 a partition, a well-defined partition? Just to check. You understood the properties. Is figure 1 a well-defined partition? No. Why? Why? What is the reason? That's true, it's not. Because there is a A2 and A3 are not disjoint, they're overlapping, right? What about figure 3? Figure 3 is a valid, right? Because there are three partitions, okay? None of them are overlapping. A3 is just this, A2 is this, and A1 is this, and their union is giving you the set. Okay, so it is. What about last one? Is A1, A2, A3 a valid partition? No. That's correct. And what is the reason in this case? Exactly. Empty space means some elements of S are not covered. That is, if I take union of A1, union A2, union A3, it will not give me S because these do not add up. Excellent. Okay, so I hope you understood what is a partition. Now let us try to take it forward and relate it to the equivalence class. Okay. Okay. Now if you consider equivalence relation R, okay, defined on a set S, okay, and you consider this set of equivalence classes of elements under S, it is denoted by this notation S backslash R. Okay, this is known as the quotient set of R, S by R. And what does it consist of? It consists of all the equivalence classes of S, which together make up the set S. Okay, so how do you define this quotient set? So first of all, you define a relation, an equivalence relation on a set S. Okay, so suppose that equivalence relation is R. Okay, now I define the quotient set SR as the set of all the equivalence classes of that set. Okay, so that means suppose set S has three elements 1, 2, 3, then set of all the equivalence classes of each element, that is set of 1, 2, 3. All the three equivalence classes will together make up my quotient set. Okay, and if some of them are same, suppose 1 and 2 are same, then I don't have to repeat it because set does not have repeated elements. I'll just write 1 and 3. So basically, collection of all the equivalence classes of a set is known as quotient set of R. Okay, and we'll see shortly how is it related to the partition. Okay, so let us see now how is it related to the partition. Okay, so before that, before I come to relation with the partition, some properties that you should always you remember and you can easily note from the equivalence classes is follows. Okay, first property is that if we consider any element A in S, then element A is always in its equivalence class. Okay, and why is it so? We discussed it in the beginning only, that if we consider equivalence class of any element, the element should itself always be present, right? What is the reason behind this? Yes, class. Why it's assured that every element will be part of its relation? Excellent. Because of the reflexive relation, right? Because A comma A pair will always be in R because equivalence relations are reflexive. The second important property is the equivalence class of two elements will always be equal if you find a pair in the relation. Okay, if any time you have two pairs of elements whose relation or whose ordered pair is in the relation, then you will see their equivalence relations, equivalence classes are always same. Okay, as you can, as we'll see again in this example. And second is, if the equivalence class of two elements is not same, then it will always be disjoint. This is a proven fact. Okay, so what are the facts? First is, every element will always be part of its equivalence class. Second is, if you ever see any ordered pair of form A comma B in R, then the respective equivalence class of these elements will always be equal. And by always, I really mean always. There is no exception to it. Okay, and if suppose there are two equivalence classes of the elements which are not equal, then they will never have any common element. They will either be equal or they will be disjoint. Okay, so these two properties will be there. Either the equivalence class of two elements will be exactly equal or they will be disjoint. Okay, they will, intersection of these will always be 5. They will never have any common element. Okay, is that clear? Right? So does it remind you or does it relate you to something, the two properties? These two properties that I mentioned, that they are either equal or they are disjoint. Does it relate to anything which we studied just now? Very good. Partitions, right? Partitions, they are always disjoint, and if they are equal, if they overlap, they will be equal. They can never overlap, right? And that is where partitions and equivalence relations combine. Okay, so if you have a relation R, an equivalence relation on a set, then all the equivalence classes of that relation actually form a partition. Okay, which means their union will give you the set itself and their intersection will be 5. Okay, so given a relation on set S, if you write all its equivalence classes, okay, so that actually forms the partition of the set S. Okay, is it clear? The two parts of it. Okay, one is if you are given an equivalence relation on a set S, okay, and you consider its quotient set, okay, or you consider a collection of all its equivalence classes, it will actually form the partition of it. Okay, and by partition I mean the three properties. They will be non-empty, they will be disjoint, and their union will give you the set itself. Okay. Okay, like let us go back to the same example that we had seen earlier, which is the equivalence relation. So if you recall, when we wrote the equivalence class of 1 and 2, they were found to be equal. Okay, and why is it so? Because of this property. Since 1 comma 2 is in R, so if you draw the equivalence class of 1 and 2, it will be same, right? But since 1 comma 3 is not in R, so you can see equivalence class of 3 is different. And if you take its intersection, it is 5, right? But when we added 2 comma 3 to it, and as a result, we had to add many other pairs, what happened? What were the resultant equivalence classes? Remember, they were all equal. Okay, why is it so? Because of this feature that either the equivalence classes are going to be disjoint or they're going to be equal. Okay, so this is how it follows from there. Right, now can you tell me what is the quotient set of S with respect to this relation R? Okay, remember, quotient set is set of all the equivalence classes of the elements in set. Okay, so can you tell me what is the quotient set for this case? Remember, quotient set will also be the partition of the set. Right, so what is the quotient? What are the sets which form the quotient set of it? Yes, class? So there are two sets we have, right? 1 and 2 and 3, right? So that is what actually will form the quotient set or partition of it. Okay, because 1 and 2 are same. So in general, it would have been like this. If you have to write the quotient set of any set, it is basically the equivalence class of all the elements, that is 1, 2, and 3, right? But since 1 and 2 are same, so you can just replace them by one of them. Okay, and this is your quotient set. It's simply the set of all the equivalence classes. Okay, and we can see it also forms a valid partition on this set, right? Because if you take the union of the two, 1 and 3, it will give you the set S, right? Because this is 1 comma 2 and this is 3, which is your set S. Okay, and their intersection is phi. Thus, is this clear? Is this clear? What is the quotient set? And how is partition related to equivalence classes? Yes? So I just got reply from two people. Is this clear? See, it's somewhere, it's unclear. I'll repeat it. It's okay. It's clear to everyone? Okay, I'll just quickly summarize before I move to this last question. See, first thing we discussed was what is a equivalence class, right? Then we defined something called quotient set. Okay, what is a quotient set? Quotient set of a set S with respect to relation R is set of all the equivalence classes. Okay, for where all elements belong to the set S, right? Now, then we related it to partition. Okay, so what we said is if we consider the quotient set of R, it actually forms the partition of that set. Okay, and by partition we mean that you divide or the partition your set into subsets which have three properties. They are non-empty, their intersection is phi, and last is their union. If you take the union of all of them, it gives you the set itself. Okay, and we see that equivalence class satisfies these three properties. Okay, like how does it satisfy that it will always be non-empty? Anyone? See, all these two properties are clear because of these two, right? But how do we satisfy that each of the partitions is non-empty? If we map partitions with the equivalence class, how do we ensure that each of these sets is non-empty? Yes, class? How do we ensure that there's at least one element in every partition? Okay, note that when I say partition, I mean each partition is equivalent to equivalence class of some element, right? So how do I ensure it has at least one element? Anyone? Nobody? It comes directly from this property. We know that if I draw equivalence class of any element, it will at least have the same element. Okay, by that I am ensured that it will never be empty. Okay, is that clear? So the three properties of partitions comes from the three property of the equivalence class. Okay, is that clear? How we ensure that each partition is non-empty? Class, are you able to hear me? Yeah, so say yes or no. Okay, great. Okay, so let us move to the last question example that I have shown here. So the question is kind of, I'm trying to cover diverse questions. So in first question, I had given you a relation and asked you, tell me what are the equivalence classes, tell me what are the quotient sets. Okay, now the question is in reverse order. Okay, the question is as follows. You are given a partition of a set S based on relation R. Okay, so the partitions are the three partitions. Okay, you have three partitions A1, A2, and A3 defined by these sets. Okay, on a set S. Okay, now what you need to tell me is what is the possible ordered pairs in the R. Okay, so it's the ulta question. There you had R and you had to tell me equivalence classes. Here I have given you the partitions or the equivalence classes, and now you need to tell me what are the possible ordered pairs. Right? Can everyone attempt it? So basically, how do you get equivalence class? You see all possible ordered pairs. So equivalence class of any element is all possible ordered pairs elements such that ordered pairs of A comma S are in R. Okay, so Yasir, Shogun have tried. Okay, so the best way to do it is, let's take one partition at a time. Okay, let's take A1. Okay, if I take A1, what are the possible pairs I have? Okay, Usad, let's start with A1 first. Okay, if I have A1, so I know I have 1, 1, I have 1, 2, I have 1, 3, right? And I have 2, 1, 2, 2, basically all possible combinations of 1, 2, and 3. And 2, 3, I have 3, 1, 3, 2, 3, 3. Okay, so this is it, right? These are the ordered pairs I will get from A1. Is there anything else? Remember, you have to take all possible combinations because I've not written the smallest or any other relation. You have to give all, you have to ensure it's an equivalence relation and all possible pairs are there. Right? So A1 gives you these. Okay, so Hasib has written the full. Let's do it stepwise. Then I have A2. So what all pairs will A2 add to it? So what are the all possible combinations I can get from 4 and 5? Very good. I have 4. So it's incomplete, Isika. Remember, it's an equivalence relation. So reflexive pairs to 4, 4, 4, 5. Then I have 5, 4. Very good. 5, 5. Excellent. What about the last set? What pairs will it add? A3. Just 6, 6, right? Because there's no other pair. Okay. Is this clear? Both ways? Okay. Either you are given a relation and you are asked to find the partition or the equivalence classes, or you are given partition and equivalence classes, you have to find the ordered pair. Okay. Is this clear? Both questions? Yes, class. Is this clear? Both the questions? Both directions? Okay. Excellent. Okay. So let us proceed further. What we discuss now next is again a very important relation which is known as a partial order relation. Okay, so let us see how partial order relation is defined and what is its significance. So a relation R on a set S is said to be a partial ordering or a partial order if it follows or satisfies these three properties. It's reflexive, that is, you have all pairs of form A comma A in R for all A in the set S. It is anti-symmetric, not symmetric. Okay, that is, if you have pairs A comma B in R and B comma A is also in R, then A and B should be equal. Otherwise, it's not anti-symmetric, and it is transitive, right? Which means AB is in R, BC is in R, then AC should also be in R. Okay, so if there's a relation which is reflexive, anti-symmetric, and transitive, it is known as a partial ordering or partial order. Okay, and the set on which this relation is defined together with this partial ordering is known as partially ordered set or poset. And poset are extremely important in computer science. Okay, so what is poset? Poset is the combination of the set together with its partial ordering relation. Okay, so that means if R is a partial ordering relation defined on set S, then the combination of S and R is known as a poset or a partially ordered set. Okay, and members of S are known as elements of poset. Okay, so in general, what we have is we generally denote the poset by this. It's not sharp line like we have in greater than or less than sign, but it is like kind of a little twisted. Okay, so this symbol is normally used to denote if A and B are members of a poset. Okay, and you can see this symbol is very similar to your less than or equal to. Okay, and the reason for this is because less than and equal to is a poset. Okay, it's a partial ordering, right? Because we know this is reflexive. Every element is related by this, and if A is less than B and B is less than A, we know then A is equal to B. That means it's anti-symmetric. And if A is less than B, B is less than C, we know A is less than C. Okay, so less than or equal to is the best example of a partial order. Okay, that's why whoever defined this relation, they use the symbol which is very close to less than equal to. Okay, So this is your partial order. Can you think of any other example which is a partial order? Any other relation which is a partial order? Okay, remember it should be reflexive, should be anti-symmetric, and it should be transitive. Any other relation that you can think is a partial order? Yes, sir. No other relation? Okay, so let us see. Subset is also a partial order, right? Because uh, it's also partial ordering because it's reflexive, that is every set is subset of itself, and it is also anti-symmetric because if A is subset of B and B is subset of A, what does it mean? If I have A is subset of B and B is subset of A, what does this mean? Right? So that means it is anti-symmetric also, and we already know it's transitive because if A is subset of B, B is subset of C, then A is subset of C. Okay? So less than equal to subset, all these are partial orders. Okay? So if I define any set S with these orderings, S subset equation or S with less than equal to, it's known as a poset. Okay, so what is a partial order? A partial order is something which is reflexive, it is anti-symmetric and transitive. Okay, let us, Faisal had asked this question, let us argue it, okay? So if considering the relation is congruent to, okay, let us see, is it a partial order or is it something else, okay? So suppose we consider triangles A. So A is congruent to A, okay? If A is congruent to B and B is congruent to A, does it mean A is equal to B? Yes, Faisal? Does it mean A is equal to B? See, transitive is also simple. If A is congruent to B and B is congruent to C, then we can say A is congruent to C. But what about this one? This is the tricky one. Is it true? What do you think? Is this true? If A is congruent to B, B is congruent to A, is it true that A is equal to B? Yes or no? Yes, class, come on. It is a common geometrical question. Okay, so in general, it may not be true, right? Because the two triangles may not be exactly same. Right? There's no guarantee they're equal. You can have two triangles which are congruent to each other. It's a symmetric relation. It's not anti-symmetric. What you require for anti-symmetric is if they are related, then they should be exactly equal. See, in subset, we guaranteed know that if A is subset of B and B is subset, they are exactly equal, right? You can have, say, two triangles, if I assume this congruentation on triangles, which are congruent to each other, but they're not exactly equal, right? Exactly, this is the best example. If their sizes are different, but ratio is same, right? So you can have two triangles which are congruent to each other, but they're not exactly the same. A equal to B, they should be exactly the same, right? Any other relation that you can think is a partial order? Yes, class. Any other relation? So before I move ahead, it would be good to see is this clear? Any other? Yes, similarity. Okay, let us see similarity in this sense. Is similarity a partial order? What do you think? Just argue argue by discussing whether it reflects, whether it is. Yes. So similarity. What do you think about similarity? So you define similarity on what? Triangle. So try to see, is it reflexive? So reflexive and transitive are same, but you have to guess on this. Uh, so it depends on what set you define. Like the thing is, when I talk about subset or less than equal to, for all sets, I'm guaranteed it is partial order. Okay, but congruence, in general, it may not be true, right? But I can tailor it. Like suppose I tell you set of triangles who have particular size. Okay, so suppose I restrict set S to set of triangles which have same size, like the all sides are same. In that case, it may become a partial order. Okay, so where I am restricting my set to be a specific case of set of triangles, not in general. Similarly, in similarity case, if I restrict my set on which I am defining this relation to some tailored set, wherein I am restricting the conditions such that this ratio and all do not differ. In such a scenarios, I can make it a partial order. Okay, that is, you can define partial order relations which are based on congruence modulo, but in general, it may not be true. Okay, so I think I'll stop there. Any questions? We'll continue discussion about different kinds of ordering, like Cauchy order, total order, in the next class. Okay, any questions, class?